Welcome to a lesson with Dr. Powell. Let's take a look at a proof of a particular fact about how we can um, see when a Hamiltonian cycle exists in a graph. So a Hamiltonian cycle is a path through a graph that begins and starts at the same point, and it's only going to hit each vertex exactly one time. Except at the beginning, it's going to hit it twice. So it's going to come around, it's going to hit each vertex one time. It's not going to go back over here to hit that again, but it's going to hit the one we started at again. We're just twice there and once everywhere else. So if our graph is simple, meaning it doesn't have multiple edges between things, like this, it's undirected in particular, it's connected, so it's completely connected from one vertex to another, and it has at least 3 vertices, has no loops like this, or self-loops at a particular vertex, and the degree of each vertex is actually fairly large. It's at least half of what the number of vertices are in the graph. These conditions right here are enough. Now, albeit this might be overkill conditions, but if these conditions are satisfied, then we can be sure that we can find a Hamiltonian cycle. And we're going to work through a little proof of that fact. Okay, so we're going to let G be the type of graph we're talking about, and we're going to take a path P of longest length in G through edges that we encounter each vertex exactly one time. So, we label the path by way of vertices, but there's edges between them as we go along. Between V1 to V2, there's an edge and so forth. But we've made a path of the longest length that's possible of doing this, so there's no cycles in that path. So we're not going to wrap around itself, but that each vertex is hit once. So this is the longest length path that has the property that we're hitting each vertex just one time. And this is possible to do if we have a finite graph. Okay, so we're going to assume that we have a finite graph, and so such a thing will be possible. Now, with our assumptions here, let's think. The path P, so that such a maximal path P, contains all vertices adjacent to V1 and all the vertices adjacent to VL. So VL is the last guy, V1 is the first guy, and everything that's adjacent to V1 should be in this path. Well, how can we be sure? Well, if it weren't, think about it, then we have something over here adjacent to it that's not in the path, and we can draw an edge between it. Look, we just made the path bigger, and we're only hitting each vertex one time. That's a contradiction. So any adjacent vertices have to be in the path itself somewhere along the way, all of them. And we know that there's at least n over 2 of them. So so a lot of these guys are actually adjacent to V1, and a lot of these guys are actually adjacent to VL as well. We're going to look at that in a minute. Another thing we actually know that the length of this path is at least 3. How do we know that? Well, for one, let's just look at vertex 1. We know it has vertex 1 in it, and it has everything that's adjacent to vertex 1, which is at least n over 2. And we also know, by assumption, that n is greater than or equal to 3. We assume that at the beginning. So, well, that means that we've accounted for at least 3 halves plus 1. So, in other words, round up to the nearest integer there. So 2 plus 1, 3. We've accounted for at least 3 vertices. So given our setup, we know that this path has to be at least size 3. Okay. Now let's take a look and see what we can do with that. We're going to look at pairs of things as we move along from V1 to VL, adjacent ones as we go along. How many pairs are there? Well, starting from here to here and so forth. Notice you have to have 2 at a time, and at the end, the last one um, stops right here. So we have n minus 1. So wait a minute. N minus 1 total pairs possible is what I should say. We don't know if it's exactly okay. So n minus 1 total pairs possible. Okay, we know that because the that's if we actually had all the vertices in here. I mean, if we didn't, then then it would be less. But it's going to be one less than the number of things in our list from V1 to VL. Okay, so we know that. So we know for sure that the number of total pairs is actually less than or equal to n minus 1. Okay. Now, if we're taking a look at that, maybe we could say, okay, and we're well, in the maximal case, I guess, if there were n things, then there would be, uh, we know that there's, wait a minute, we know there's this n over 2 different vertices that are actually adjacent to V1, right? And we know all of them are actually in this list. Okay, so we know n over 2, and we also know that they don't include V1 because there's no self loops. So they have to be like second positions, right? So like a second position. So there's actually n over 2 pairs such that the second position is going to be adjacent to V1. And if we're just looking at the second position, then that's going to count individually for each one distinctly. That's adjacent to V1, which we know there's at least n over 2 pairs. They could even be more. Okay, so we know we have at least n over 2 of these pairs in this list, even if we haven't used all the vertices. But we know at least n over 2 of the pairs are going to have the second guy being adjacent to V1. And in a similar way, we know that everything adjacent to VL is actually in there, and it's going to occur as a first of one of these adjacent pairs. So we know we have n over 2 of those guys. Now, we know that these collections of pairs adjacent like that or like this cannot be disjoint, because if they were, then there would be a total of wow, we'd know we'd have, this is at least that many, then that we'd know we would have like over n pairs in here. But we know n minus 1 is a total possible, so it has to have an intersection. There has to be a pair where we have this going on. This is linking to that, and this guy right here has to be linking down to V1. So we have this crossover. Now, if you have a crossover like that, look what we can do. We can actually go from here to there, around, down, down, down. We have just turned our maximal path P into a cycle, and we didn't even add any extra vertices in, but we made it into a cycle using the edges that are actually in the graph. So there's a cycle, so if we have a maximal path, we actually turned it into a cycle. But what's neat about that cycle is that every single, that we could actually break it at any point, like have any point be like the beginning of the path, and the other point being the ending of the path. That would be another version of P, which means that in this path itself, like if we were to erase this, that that this path contains everything that is adjacent to this guy and everything adjacent to that guy. Okay, so basically this path contains everything that's adjacent to all of the vertices in the path. Okay, so if it contains everything that's adjacent to every vertex in the path, okay, the question is, does that contain all of the vertices in the graph G? Well, we know G is connected. Okay, and so thinking about that, okay, so since G is connected, all right, so maybe there's some vertex over here, all right, let's think. Would this vertex be included in this list? Well, okay, well, let's suppose that there's some path, all right, that goes to that vertex out there. All right, but you see this guy? this guy is contained in here. And wait a minute, if this guy's contained in here, then that means that guy's contained in there. Which means that guy's, oh, everything's in there. So we actually have been successful. We have this path that hits every vertex once, and it contains every single vertex in a graph. Thanks for watching.